Welcome back to AI.Code.Cast. Today, we're going to be doing a deep dive into this data structure called Randomized Set.
Yeah, so this is a really cool one. It seems simple at first, but there's some pretty interesting stuff going on under the hood.
I've definitely heard this one come up in interviews before, so definitely something worth knowing.
Yeah, absolutely. And I mean, even beyond interviews, the concepts here, they show up in real world algorithms, like Monte Carlo methods that you might see in AI or machine
Oh,
learning.
wow. Okay, so we're not just talking about like theoretical textbook stuff here. This is like
Mhm.
actually used out there in the wild.
Right, exactly. Like if you're ever working with those kinds of algorithms, understanding this kind of data structure can really give you an edge.
Gotcha. Okay. Well, then let's not waste any more time. Let's jump right in. So, what exactly is a randomized set? What makes it so special?
All right, so at its core, it's a set, right? So you can store a bunch of items in it. But here's the twist. You need to be able to do three things with it, and you need to be able to do them all really fast.
Really fast, meaning like constant time. Oh, one.
You got it. So operation number one, you got to be able to insert new elements into the set.
Okay, so like add a new number or a new name or whatever to the set. Got it. What's number two?
Number two is you need to be able to remove elements that are already in the set.
Okay, makes sense. So far, we've got insert and delete. Anything else?
Yep. The third, and this is where it gets interesting, is you need to be able to get a random element from the set, and it has to be truly random. Every element has to have an equal chance of being picked.
Oh, okay. I see where the randomized part comes in. So basically, we're trying to build a set that lets us add stuff, remove stuff, and pick something random from it all in constant time.
Right on. And you might be thinking, well, that doesn't sound too hard. Can't we just use an array or something?
Yeah, I was going to say an array would make picking a random element pretty easy. Just pick a random index and you're done.
True, but think about what happens when you try to insert or delete something in the middle of an array.
Oh, right. You might have to shift a bunch of other elements around to fill the gap or keep things in order.
Exactly, and that shifting can take up to O(n) time, where n is the number of elements in the array. So suddenly our beautiful constant time dreams are shattered.
So an array on its own won't cut it. This is already getting tricky. What other options do we have?
Well, we need something that's good for both fast insertions and deletions, but also something that lets us access elements randomly in constant time.
Hmm. I'm racking my brain here. Any hints?
Well, think about data structures that are known for their speed. What's really fast for lookups?
Let me think. Well, hash maps are super fast for lookups, right? Almost instant.
They are. Now, what about something that lets us go through elements one by one sequentially?
For that, maybe like a linked list or an array list?
We're getting warmer. What if we could somehow combine the strengths of a hash map and an array list?
Combine them. Interesting. Okay, now I'm really curious. Tell me more. A hash map and an array list. Okay. I'm intrigued. How does that help us solve this randomized set puzzle?
All right, so let's say we want to insert the number 5 into our randomized set. First things first, we got to check if 5 is already in the hash map.
Makes sense. No duplicates allowed.
Right. At least not in this version. We'll get to duplicates later.
Huh.
But if it's a brand new element like 5, then we need to add it to both the hash map and the array list.
Okay, and we're adding it to the array list because that gives us that nice sequential order that we can use for random selection.
Exactly. We'll just stick it at the end of the array list, nice and easy.
Hmm.
And then in the hash map, we store 5 as the key, but the value is where the magic happens.
Okay, so the key is 5. What do we use for the value?
The value is the index of 5 in the array list. So in this case, since we just added 5 to the end of the array list and it's the first element, its index would be 0.
So the hash map entry for 5 would be 5, comma 0. Got it.
Q, got it. So the hash map is like our super fast index. It tells us exactly where to find an element in the array list.
Okay, so far so good. Now what about deletions? What if we want to get rid of that 5 that we just added?
All right, so first we use the hash map to quickly find 5 in the array list. Let's say by now it's moved to index 2. Maybe we added a couple more elements.
So we know 5 is at index 2.
Yeah.
Now do we just delete it from the array list?
Well, we could, but remember, deleting from the middle of an array list can be slow because we might have to shift a bunch of elements to fill that empty space.
Oh, right. We don't want to mess up our beautiful O1 time complexity.
Exactly. So instead of deleting directly, we do a little swap trick.
A swap. Okay, I'm listening. What are we swapping?
We swap 5 with the very last element in the array list. That way we're always deleting from the end, which is a super fast constant time operation.
Clever. But wait, doesn't that mess up our hash map? Now the element we swap with 5 has a new index.
Good catch. You're absolutely right. We got to update the hash map to reflect that swap. So we find the element we swapped with 5 and we update its index in the hash map.
Okay, so the swap keeps the array list deletion fast, and the hash map update makes sure everything stays in sync. I love it.
It's all about using the right tool for the job.
Okay, so we've covered insertions and deletions. Now what about the star of the show? How do we actually get a random element from this setup?
This is the fun part. It's actually surprisingly simple. We just generate a random number between 0 and the size of the array list, minus 1, of course.
Okay, and that random number becomes our index.
You got it. We take that random index and we just return whatever element is sitting at that index in the array list.
And since the array list is keeping all our elements in order and we're picking a truly random index, every element has an equal chance of being chosen.
Bingo. We've cracked the code. We've got all three operations, insert, delete, and get random, all happening in average 01 time.
This is amazing. But I gotta ask, are there any sneaky edge cases where this might not work so smoothly?
You're right to be cautious. There's one thing we haven't talked about yet, array list resizing.
Ah, yeah. What happens when our array list gets full and needs to grow?
So when an array list hits its capacity, it's got to create a new, bigger array and copy all the elements over, which takes on time.
Oh, so that means insertions could sometimes take linear time if they trigger a resize.
Technically, yes. But in practice, array lists are pretty smart about resizing. They usually double their size when they get full, so resizing happens less and less often as the array list grows.
So it's like a rare but expensive event. But overall, the average time complexity stays nice and low.
Exactly, it's amortized 01, so we don't need to worry too much about those occasional resizes.
This has been a fantastic deep dive into handling unique elements in a randomized set. But I can't help but wonder, what if we wanted to allow duplicates? Would our approach still work?
That's a great question, and it leads us to some even more interesting modifications. To handle duplicates, we got to tweak our hash map just a bit to keep track of those multiple occurrences.
All right, so duplicates, huh? Sounds like things are about to get a bit more complicated.
Yeah, you can't just toss duplicates into the mix without shaking things up a bit. Remember, our hash map can only store one index per element, right?
Right, so if we have like 3 copies of the number 5, we'd only be able to store one of their indices in the hash map.
Exactly, and that would throw off our whole system. Our get random wouldn't be truly random anymore because some duplicates would have a higher chance of being picked than others.
Okay, so how do we fix that? How do we make sure all those duplicates get a fair shake?
Well, we got to give our hash map a little upgrade. Instead of storing just a single index as the value, we're going to store a whole list of indices.
A list inside the hash map. So like if we have 3 5s at indices 2, 5, and 8, the hash map entry for 5 would be a list containing those 3 indices.
Exactly. That way we can keep track of all the spots where a duplicate element is hanging out in the array list.
I see. So that solves the storage problem.
Yeah.
But what about deletions? If we want to delete one of those 5s, which index do we remove from the list in the hash map?
Now this is where we got to be careful. We want to make sure we're still maintaining the randomized part of our set.
Meaning we can't just always delete the first index in the list, right?
Yeah. Right. If we did that, the duplicates at the beginning of the list would always be more likely to get deleted than the ones at the end. So instead, we're going to randomly choose an index from the list to remove.
Okay, so we pick a random index from the list,
Right.
remove it, and then delete the corresponding element from the array list. That way, every duplicate has an equal chance of getting the axe.
Precisely. We're preserving the randomness and keeping our set nice and unpredictable.
Love it. Now, does this change how getRandom works at all?
Not really. It still works pretty much the same way. We generate a random index from 0 to the size of the array list and return whatever element is at that index.
But now that index could point to any of the duplicates, right?
Exactly. And they all have an equal probability of being chosen because we're picking the index randomly.
Wow. So we made this one little change to our hash map, and now our randomized set can handle duplicates like a champ, all while keeping that beautiful O1 performance.
It's all about understanding the strengths and weaknesses of our data structures and using them in clever ways.
Well, I think we've pretty much covered everything there is to know about randomized sets, from handling unique elements to tackling those tricky duplicates. It's been a wild ride.
It has. But the learning never stops, right? So here's a little something to ponder. We focused on average O1 complexity today, but how would you go about guaranteeing worst-case O1 time for all those operations? It's a tough one, but a good challenge to keep those coding skills sharp.
That's a great question to leave our listeners with. And with that, we wrap up another episode of AI.Code.Cast. Thanks for joining us on this deep dive into the world of randomized sets. Until next time, happy coding.